right, good morning, everybody. The first topic of today's lecture is something called class invariants. So if you ever hear the term invariant, it's a condition that is always true. So a class invariant is a condition that's always true regarding the state of an object. Right? So if you have a class, say counter, our counter class, right? If that class has some invariants, then every counter object has something about its state that's always true. Right? So establishing the invariant has to be done when the object is created. Right? So the constructor, when it initializes the state of the object, has to ensure that the state of the object is such that the class invariants are true. Right? Every public method that runs must also do the same thing. So when the public method finishes running, the class invariants must also be true for that particular object. Now, while the method is running, it's not necessarily the case that the invariants are true. Right? So only when the method is done running are the invariants established. Many classes have no interesting invariants. Right? So not every class has an invariant. So for example, point 2, it's just a point. Right? So it's got an x and a y coordinate, and there's nothing special about the x and y coordinates. Right? The value of x and y can be any legal double value. So that's not considered to be an interesting invariant. Right? The fact that the coordinates are of type double is not considered to be an invariant. Or at least most people would not consider it to be an invariant. The counter class that we looked at a couple of weeks ago does have an important invariant. Right? So remember, the counter promises that its value is never 0. Right? And it always counts up to, and including integer max value. So its invariant can be expressed as the value of the counter is always greater than 0 and less than or equal to the maximum integer value. If you actually look at the implementation of the counter class, you can actually see that this is true. Right? So for example, the no argument constructor sets the value of the counter to 0. Right? 0 satisfies the class invariant. Right? The advanced method always checks before it adds 1 to the value of the counter, it checks if the value is already integer max value. If it's integer max value, it sets the value of the counter to 0, so it wraps around back to 0, which again ensures that the invariant is always true. Right? And then some of the methods don't do anything. So for example, the value method simply returns the value of the counter, so it never changes the state of the counter, which also leaves the invariant as being true. In your current assignment, if you had a chance to look at it, there's this class called interval. Interval has some invariants. Right? So if you read the documentation for the class, it says it's a closed integer interval containing all integer values between some minimum and maximum values. Right? And so that means that the width of the interval is always at least 0 or more. Right? So that's the invariant here for this class would be the width of the interval. Right? There's some minimum value, there's some maximum value, and you're told that they're integers, so it has to be some finite width. It also promises to ensure that the minimum and maximum values are always always representable as int values, which in this case is significant because you can move the interval around. So you can imagine if you move the interval too far left or too far right, one of its ends might fall off the range of int, and so the class makes sure that that never happens. Okay, so the invariants must be true at the end of every constructor and every public method. If you really wanted to, you could in fact check your invariants at the end of every constructor and public method. And so one way you could do this is using what's called an assert statement. So an assert statement is simply the word assert, and then it's followed by a condition that you think is true. If the condition is not true, then the assert statement throws an error. The assert statement causes an error to occur, which effectively causes an exception to occur. Now, compared to using a plain old if statement, assertions can be turned on or off when your program is compiled. And so you can use assert statements when you're developing your code and turn them on. So this will help you debug your code. So for example, you might want to check the class invariants at the end of every method while you're developing your code. Right? When you're done and you're convinced your code is more or less correct, and you decide to ship your code, you can turn assertions off. And so that way people who are using your code don't have to pay the price of testing for the assertions every time. So in Eclipse, if you want to do this sort of thing, they're turned off by default. So if you try to do this in Eclipse, by default, nothing happens. And so your assertions will never be checked. So if you want to, you can follow these instructions here and turn them on in Eclipse if you like. Right? Here's an example of using them. So this is for the counter class. So remember, the class has the invariant that the value is always greater than 0. Right? The value is already represented as an int, so I never have to test if it's greater than integer max value. Right? It's impossible for it to be greater than integer max value. So I can write a little private method called check invariant. Right? And the check invariant method simply has an assert statement in it. Right? It simply asserts that the value is always greater than or equal to 0. If there's ever a time when you call check invariant where this is not true, an exception will be raised. An exception will be thrown. Right? And so the way that you would go about testing or checking your invariants is at the end of every constructor and method, you would just call your check invariant method. Right? So their counter constructor here sets the value of the counter to 0, checks the invariant. Right? This constructor here sets the value to whatever value the user passed in, as long as the value that the user passed in is actually greater than or equal to 0. Right? And then it checks the invariant. Right? And so on and so on and so on. It's the same thing every time. Right? You're just going to call check invariant at the end of every public method and constructor. So you could do this. No one does it. I would say not many people actually do this in Java. Again, to repeat the point from the last lecture, there are languages that do check your invariants for you automatically at the end of every public method or constructor. Java is not one of those languages. Okay, so that's all we need to say about class invariants, right? It's just some condition that the class promises is always true. Will always be true for every object belonging to that's made from the class, right? It's true when the public methods and constructors finish running. Okay, any questions about, yes, question? Do you have to do invariants for these? No, you don't have to do, you mean do you have to check for the invariants? No, you don't have to check for the invariants. So to expand on your point, the way that we check your code does in fact check the invariants of the class. So the testing scripts that I give the TAs actually have those tests in them. Okay, so you now know how to create a class. So you know how to make a class. It's got some fields, it's got some constructors and methods. In this course, this topic is not especially important, but in your upcoming software development courses, you will see these things with increasing frequency. So there is a visual way to describe classes in an object-oriented program, or in object-oriented languages, sorry. And so the standard language for doing this is something called UML. So it's the Unified Modeling Language. So it's useful to tell you about these things in this course. All right, so UML is a visual modeling language. So it's basically pictures. And these pictures describe the structure and behavior of a piece of software. The picture that I'm showing you here is an example of UML diagram. It's a UML diagram that describes the UML language. Right? So at the top here, you can see there's this thing called diagram, and then there's a behavior diagram and a structure diagram. Right? You can imagine that behavior diagrams describe how your classes behave. Right? Structure diagrams describe how describe the structure of your classes. Right? In this course, we're mostly interested in these. And in particular, we're interested in these things called class diagrams. Right? They describe how your classes are structured. And notice there's lots of other types of diagrams that you can have in the UML language. Right? And in your software development courses, you'll learn more about these different types of diagrams. Here, we'd be happy if you just knew what a class diagram was. So a UML class diagram describes the structure of a class. Right? And so the structure of a class includes its name and its fields and perhaps its methods and constructors. Right? So in UML, it's not designed for any particular object-oriented language. So UML uses the generic term attributes instead of fields. Right? Fields is a very Java-specific term. Instead of methods, UML calls these operations, right? Okay, so that's the simplest UML class diagram that you can have, right? It's just a box and the name of the class inside the box, right? And that's the only mandatory information that you might want, that you are required to have for a UML class diagram. Right? And so the language is flexible in that it lets you show as much or as little detail as you need for the purpose of your, for the reason that you're using your diagram. Right? So there's an example of our point2 class shown as a UML class diagram. Right? If you want to, or if you have a need to, you can then show the fields belonging to the class in a box below the box containing the name. Right? So our point2 class, you can see here, has two attributes or two fields of type double. Right? Their names are x and y. The minus sign here indicates the access modifier. And so the minus indicates that it's private in our class. Right? So notice again that the language is not exactly the same as Java. Right? Again, because the UML language is not Java specific. So if you have a public field, you can use the plus sign. If you have a package private field, you can use the tilde. And if you have a protected field, you can use the hashtag or pound sign. Again, if you have a need to, you can then show one or more of your methods or constructors in a box below your fields. Right? Or you can ignore the fields and have another box below the class name that includes your constructors and methods. Right? So they look the same. The slide tells you what they look like, but it's easier just to see an example. Right? And so our class, at least as we've implemented it so far, you can see it has a constructor that's public. Right? There's our no argument constructor. There's our constructor that takes in the x and y value of the point. There's our copy constructor. Right? Notice, so for the methods, if the methods return a value, it comes after the name of the method. Right? So x round bracket, colon double says that the method x returns a double value. Right? Again, the plus sign means that the method is public. So there's nothing complicated about these UML class diagrams. They're there to convey, the intent of these diagrams is to convey the relevant information for your class. If your class implements an interface, so remember we did talk a little bit about interfaces a couple of weeks ago now, you can show that they implement the interface using what's called the lollipop notation. So you might recall that an array list is or implements the list interface. So the way that you would communicate that in your class diagram is you draw the box for array list, right? And then there's a solid line and a little circle, and then the name of the interface that the class implements. Right? Where you draw the solid line and circle, it doesn't matter as long as it's attached to array list. So for example, treeset implements the sorted set interface. Right? And later on in the course, you'll be creating classes that actually implement interfaces that we create. Oh. Right. So there's nothing difficult with these UML class diagrams, but it's useful to introduce them here. Sometimes on an assignment, you'll be given a picture of the UML class diagram, or the class diagrams for one or more classes in the assignment. Right? And it's there to help you visualize the structure of the assignment that you're trying to complete. Right? In larger pieces of software, they try to show you the structure of the overall program, or parts of the overall program. Okay. Any questions about UML class diagrams? Great. So the next topic is static features. So remember when we started this course, everything was static, right? All of our methods were static. There were some fields that you had to use that were static, right? And then we switched to, well, everything's non-static now, right? All the constructors are non-static. We started implementing methods that are not static. We had fields that were not static, right? And now we're coming back to the static features. So a class is allowed to have both static and non-static features, right? So there's no reason you can't mix the two. Right, so you can have fields and methods that are static. Right? So remember what the difference is between static and non-static in Java. right, a static feature belongs to the class, right, instead of belonging to individual objects. Right, so if you have a field that's static, it belongs to the class, right? There's only one copy of the field, right? If you have a method that's static, again, it belongs to the class. When you use the method, you use the name of the class to call the method. So static fields are what are called per class members, right? One per class. Only one copy of the field exists, right? And that field is associated with the name of the class. Right, and so what does that mean? So that means if you have an object that's created from the class, then all objects that are made from the class share the same static field. Right? So they're also called class variables to emphasize the fact that they belong to the class and not to individual objects. Right? Non-static variables are often called instance variables to indicate that they belong to individual objects and not the class. Right, so let me just jump into Eclipse for a quick second. Okay, so here's point 2, right? Notice that our fields are not static. Okay. Suppose you, so a not uncommon error is to make these static, right? And so if you make them static and you write a little test program, everything will probably seem to work. So for example, if I stick in a main method here, right, so can I make a new point? Let's try it. Point 2p equals new point. Right, no red, so Eclipse is happy with this anyway. Can I print out the point? Right, so can I use toString to generate a string representation of our point p? Well, let's see. The answer is yes, it seems to work. Right. Okay, so let's make a new point. Let's see what happens. Point 2q. I just need to check if I have the second constructor in here. I don't. Okay, so let me quickly insert the second constructor. Right, so our second constructor is simply this x equals x, and this y is equal to y. So let's try to use the second constructor and make a new point. So 1.5 and 2.5, and we'll print that out too. Right, and that also seems to work. So at this point, many programmers new to Java will say, well, my class is correct, and I can just make all my fields static. Right, and so of course the problem is that there's only one copy of the fields x and y. Right? So if I now print out p, suddenly p is now 1.5 and 2.5. Right? It's no longer 0 and 0. Right? Why is it no longer 0 and 0? It's because in your entire program, there's only one thing called x. There's only one field belonging to point 2 called x. There's only one field belonging to point 2 called y. And so what this means is that all your points have the same x and y coordinate. In fact, you only ever have one point, right? And so that's why for most classes the fields are typically not static, right? Typically, a class is made to make objects. Every object needs to have its own state. Right? By marking the field as being static, you're saying all objects share the same state with regards to this field. Right? So these can't be static. Right. So you put them back to non-static and you run your program, and now P maintains its own state. Right. All right, so you might guess that static fields are not very common in classes, and that is true. Right. If there's only one copy of the field, you're trying to say something fairly significant. Right. You're saying there's one value that's important to all objects of the class. If you haven't seen a domino, so dominoes are these little tiles that you can play a variety of games with. Each domino has two faces. Each face is marked with a number of dots called pips, right? And you can have anywhere from 0 to 6. Yeah, 0 to 6 pips in a standard set of dominoes. And variations of these tiles have different numbers of different possible numbers of pips. But the standard set looks something like this. Right, so you've got a domino that has 0 and 0, and you've got one that has 6 and 6, and you've got one for everything in between. So if you decided to make a class that represents dominoes, you might decide that, hey, it's important people know what the minimum value for the minimum number of pips are and what the maximum number of pips are, right? You only need one copy of those fields, right? All dominoes have the same minimum value. All dominoes have the same maximum value. It doesn't make sense to have a non-static field for both of those fields, right? One is sufficient. And so here, I've got a public static final field called min value, right? So the minimum number of pips on a domino is 0. The maximum number of pips on a domino is 6, right? They're both static, indicating that these values are true for every, or these are the values for every domino object. Right? They're also marked final, meaning I can't change their value once I assign a value to them. Right? Now, each individual domino has its own number of pips, right? So that one's got 1 and 4, this one's got 6 and 6, and this one's got 3 and 3. So to represent an individual domino tile, I now need, or I could use 2 separate fields to represent the number of pips belonging to a particular domino. Right? So here we have val 1 and val 2. So for example, it might be 1 and 4 or 6 and 6 or something. Right? So these cannot be static. Right? Every domino has its own 2 sides. Right? So if you want a memory diagram for this, it looks something like the following. So when you use the domino class for the first time, it gets loaded into memory. So there it is. Right. What's in the domino class? There's a field called min value. There's a field called max value. There's some details missing here. There should also be a val 1 and a val 2, right? But it doesn't fit on the slide. So there should be a val 1 here. There'd be a val 2 here. Right? When you make a new domino object, you make a copy of the class, right? But you don't copy the static fields, right? You only copy the non-static fields, right? You don't copy the static fields because they belong to the class. So you would copy val 1 and val 2 to make a domino object here. We make a second domino object there. Right? The constructors fill in the values 1 and 3 for val 1 and 5 and 5 for val 1 and val 2. Right? So that's what it looks like in memory. Right? Class, static fields, right? Objects, non-static fields. Right? These 2 domino objects can still use the static fields. Okay, so if you decide to use a static field at any point, you should access the field using the name of the class and not the name of an object. Right? So if you want to know what the minimum domino value is, you can just write big D domino.min value, right? Just like I showed you earlier in the course. Right? Unfortunately, the language allows you to use an object reference to access static fields. It's unfortunate because it's confusing when you read code that does this. So here I make a domino object, and it doesn't matter what the values of 3 and 4 are. Right? I can then access min value using the name D instead of using the class name domino. Right? So this is perfectly legal. The compiler will allow it. Eclipse will flag a warning, so it will warn you you're using a static field in a non-static context. So you're using an object to access the field. Right? So it's legal, but bad form. You should always access a static field or anything that's static using the name of the class. Right? To experienced programmers, that clearly communicates the fact that min value is static. Right? To an experienced programmer, that reads like min value is a non-static field. Right? And it's not until later on where they actually go and look at the source code or the documentation that they realize it's in fact static. Right? And then they complain back to you. Right? So you should avoid doing stuff that looks like that. On test 1, some people did in fact access a static method using an object, which is fine. You didn't lose marks for it in test 1. Okay, so a field that is final, we've talked about this a little bit before. So when you mark a variable as being final, it means the variable can only be assigned a value once. And the same is true for fields. If you mark a field as being final, you can only assign a value to it once. So when I marked min value as being static and final, static means belongs to the class. Final means I can set its value once. So when I write equals 0, min value effectively becomes constant. Right? There's no way that you can change min value anymore. So if you ever see a public static final field, the class creator is trying to tell you This is a constant value. It's meaningful to this class, right? So min value is meaningful for dominoes. It's the minimum value for any domino, for any face of a domino. If you have a public static final field of primitive type, sorry, if you have a final field of primitive type, so in this case min value is an int, right, then it is effectively constant. Right? If you try to change the value of min value somewhere, right, the compiler will not allow it. Right? It'll tell you min value is final, it's already been assigned. Right? So this will not even compile. If you have an immutable type like string, so remember string is called an immutable type. So an immutable type is a reference type whose values can't change. Right? So a string represents a sequence of characters, and you can't change the characters in the string. Right? You can't even change its length. Right? So string is an example of an immutable type. So here I've got a public static final string. That's the string peekaboo. Right? And so what this means is that there is some string object in memory somewhere, right? And its letters are peekaboo, right? And there's no way to change those letters, right? Furthermore, the name x always refers to this string, right? I can't make x refer to a different string, right? So if I try to make x refer to a new string, I see you, that doesn't work either, right? The compiler will tell you it's final, you can't reassign a value to it, right? So I can't find the reference for this string and assign it back to x, right? X has already been assigned a value. All right, so what happens if you have a, right, string is immutable. It has no methods that can change the contents of a string. So what happens if you have something that's not immutable and you mark it as being final? Right, so here's here's a list, or an array list, it doesn't matter, right, called empty, right? And so the name of the field empty seems to suggest that this list is always an empty list, right? Which surprisingly turns out to be useful in some cases. So here I make a new array list, right? That makes a new empty list, right? I've marked it as final, so I can't say empty is some other list, right? If you try to say empty equals new list somewhere else, it's not going to work, right? It's marked as being final. But the problem here is that list is not immutable. So I can take my list and I can call any method belonging to the list, like add, which adds a string to this list, right? And that works, right? So your list that was once empty is no longer empty, and the name is now very deceptive, right? This works. So it's true, you can't assign another list to empty, but you can, in fact, change the state of the list that empty refers to, right? You can add stuff to it, you can remove stuff from it if there's something in it, and so on and so on and so on, right? And so in this case, your field empty is not logically constant, right? Yes, it always refers to the same list, but the state of the object can change, right? So you should probably avoid using mutable types as public constants, right? They probably don't do what you want it to do, although you might come across a case where you do in fact want a static field that is public and not mutable, right? And is mutable, sorry. So there probably are legitimate reasons for doing this, but you probably don't want to do this, right? Mutable types as public constants are not logically constant, right? You can change their state, and that is confusing. Okay, so that's all we need to say about public fields. Static fields. Now, what about static methods? So, unlike static fields, static methods are more common static methods are more commonly seen in classes that have non-static features. Right? So, just like static fields, static methods belong to the class, right? So they are per class members, right? One per class. To use the method, you don't have to make an object. Right? It belongs to the class, so you can just use the name of the class to access the method. So again, using the domino example, right? You can make a method called isValueOK, and this checks an integer value to determine if it is a legal domino value. Right? So is it between 0 and 6? Right? So I can make this static. Right? One of the reasons I can make this static is because I can access the fields of domino, right? The static fields of domino from a static method. Right? So static methods can use the static fields of the class. What you can't do is you can't write value less than this dot value 1 or this dot value 2, right? Or whatever I called them, right? So you cannot use the keyword this inside of a static method, right? And the answer, so you might ask, why can't I use this in a static method? And the answer is because this is a reference to the object that was used to call the method, right? That's what this means inside of a method, right? When you call isValue OK, you don't use an object to call the method. So there is no object, so the value of this is undefined, right? So you cannot use the non-static fields of a class with using the keyword this, right? Now the confusing part is that you can access the non-static fields of the class if someone gives you an object, right? So if someone gives you a domino object D as one of the parameters, right, then you can write D.value1 and D.value2, that's fine, right? But you cannot use the keyword this inside of a static method. So typically static methods rely only on the static fields of the class, although that's not always the case. All right, so if you're going to access a static method, use the name of the class, right? So this checks if the value 8 is valid, which obviously it's not, right? So this will print false. Again, just like with accessing static fields, you are allowed to make an object and then call the static method. Right? Again, Eclipse will complain, but it will compile your code and your code will run. So avoid doing this. All right, so static methods and fields show up commonly in things called utility classes, and then there's another common use that I don't know if we'll get to in this lecture. But let's talk about utility classes first, and this is very easy because you already know what one of these things is, whether you realize it or not. Right? So remember what a class is. It's a model of a concept or thing, right? It's a user-defined type. In Java, it's most commonly used to make objects, right? So that's the purpose of most classes. Every once in a while, it's useful to create a class where you do not want to make any objects using the class, right? And so assignment 1 was an example of that. Right? You had a class, everything was static, right? That's an indication that that thing is what's called a utility class, right? You're not using the class to make objects. Instead, you're using the class because it's got some methods and perhaps some fields that are useful to you. Right? So in a utility class, everything is marked as static, right? If there's anything that's not static in the class, it's not a utility class, right? And so the math class is an example of a utility class, right? The math class is just a bunch of mathematical functions and some constants, right? You don't need to make a math object to call any of the methods or to use any of the constants, right? So math is a utility class. The arrays class, which we used to get the string representation of an array, is an example of a utility class that operates on arrays, right? So it contains a bunch of useful methods for arrays, and that's it, right? You don't make an arrays object to call those methods, right? And the collections class we saw very briefly. It's got some methods that operate on lists and sets, right? And again, you don't need to make a collections object to use any one of the methods, right? You just use the class name itself. So it's got a bunch of static methods that operate on lists and sets. So the purpose of a utility class is to group together a bunch of related fields and methods where you don't have to make an object to use those fields or methods. Right? So again, math, bunch of mathematical constants and functions, right? Collections, bunch of methods that operate on sets and lists, right? So with utility classes, you never make an object, right? To use the class, right? So to use the math class, no math object, just use the name of the class, right? Only the class itself occupies any memory when you use a utility class. Right? If this was not a utility class, you'd have to make a math object, and then that object would occupy memory. Right? Okay, so how do you make a utility class? So it's very easy. There's only one thing you have, well, there's two things you have to remember. One, everything is static, so that's pretty easy. Two, you have to do something to prevent people from making objects of your type. All right, so I'm just going to implement Einstein's equation E equals mc squared. That's it. Right? If you don't know what this thing is, don't worry about it. It's just a mathematical equation. Right? M is mass in kilograms. C is the speed of light in meters per second. E is the amount of energy equivalent to that mass. So if you convert all that mass into energy, that is the amount of energy that you would get. Right? Okay, so it's just a class, so make a class. Right? If you want it in a package, make a package. Right? I'm just going to call this thing relativity. Right? So that was pretty easy. Right? If there's any reasonable constants that your class that people who are using your class might find useful, put them in. Right? Make sure they're static. Right? So here, the speed of light. So number one, it is a constant, so that's good. So it's a physical constant, so it makes sense to make it a constant in the class. Two, anybody using this class, there's a pretty good chance they want to know what the speed of light is. And so it makes sense to make this public as well. Right? So there's our speed of light. There's our E equals mc squared formula. Right? That's E, that's M, there's C. Right? So to calculate the amount of energy corresponding to some amount of mass, you just write mass times c squared. Right? And that's it. You're almost done. Right? Our utility class is almost done. Right? You can then use your class to maybe compute the amount of energy in 1 gram of mass. Right? And if you run that, it works. Right? So there's our call to our method right there. Right? And you get this number. It's like 9 times 10 to the 13 joules. Right? Anything times 10 to the 13 is a pretty big number. So this turns out to be a rather large amount of energy. So if you convert 1 gram of mass into energy, you get a lot of energy back out. Which is what makes nuclear fission useful. Okay, so, I mean, that was pretty simple, right? Class, static field, static method, right? Nothing new. There's only one hitch. Our class doesn't expose a constructor, right? No constructor. Unfortunately, you can write that, right? And why can you write that? It's because the compiler makes up a constructor for you. Right? So when the compiler sees this class, it says, hey, you've got no constructor. I'm going to stick one in for you. Right? And so it sticks in the no argument constructor for you. So in other words, it puts in the constructor that has no arguments. Right? And it doesn't do anything useful for this class. Right? The class has no non-static fields. So the constructor doesn't even initialize any non-static fields. But you get one anyway. Right? And that's just the way that the language works. Right, so you get that. That's effectively what you get, right? So if you took that line of code, stuck it into the class, basically it's the exact same class. Okay, so a utility class, you don't want people to make objects of that type. So you want to stop people from writing that, right? So how do you do that, right? So the trick is you just make a private constructor. As soon as you make any constructor in a class, the compiler won't make one for you. Right? If you make it private, no one outside the class can use the constructor. So they can't even see the constructor. Right? So you just stick in a private constructor here. It doesn't matter what the constructor is. You can put in whatever parameters you want to here. It doesn't matter. Right? Typically, programmers will put in a private no argument constructor because it's the easiest one to type. Right? And it does nothing. Right? In many cases, there will be a comment here. Right? Saying that it's private and empty by design, right? And so this is telling anybody else who comes along and who can see the source code, hey, this thing's a utility class, right? That's why this constructor is here, right? It's simply to prevent people from writing new relativity, right? And that's it, now you're done. That's a utility class, right? Everything's static, there's a private constructor, right? So every utility class should have a private, usually empty, no argument constructor, and that's to prevent other people from making objects of that type. And that's all there is to say about utility classes, right? They're very easy to make. Okay, so what about these static methods inside of a non-utility class? So static methods inside of a non-utility class are quite common. And in particular, these things called factory methods are quite common. Right? So a static factory method, so it's static. Right? It's a factory method. So factory method means that the method makes an object or objects. Right? So a static factory method is just a static method that returns an object. Right? Now it's a static method, so you can call the method using the name of the class. Right? You don't need to make another object first to call the static factory method. Right? And so if you have a method that returns an object, right, that's sort of like having a constructor, right? So remember, if you use new with a constructor, you get a new object, right, that is initialized to some state. If you call a static factory method, you get a new object that's initialized to some state. So you can use static factory methods to create methods that behave like constructors, right? Now, unlike a constructor, so remember what the restriction is of a constructor is, constructors always have the same name as the class that they are defined in. That's not true with the methods. You can name a method whatever you want, right? And so this is why they turn out to be very useful. You can provide a method that has a descriptive name that behaves like a constructor. So remember our point2 class, right? You can create a point given its x and y coordinate, right? If you've taken calculus and you've been told about what the polar form of a point is, right, you also know that a point can be described using the distance from the origin, so that's r, right? And the angle of the, if you draw the line from the origin to the point, then the angle from the x-axis to the line is the angle theta, right? You know that the coordinates of this point is just r cos theta and r sine theta, right? The point is on a circle of radius r centered at the origin. That's the polar form of the point, right? Depending on what you're making the point2 class for, it might be useful to make a point given its polar form, right? So given r and theta. So what's the problem with this in our class? Right? I've got a constructor here that takes in a double and a double, right? X and y. Right? If I want to add the constructor that makes a point given its polar form, r and theta are probably doubles, right? And so now I've got a constructor whose signature is point double double. And I have a second constructor whose signature is also point double double. And that's not allowed. Right? I've got two constructors with the same signature. So that's an illegal overload. Right? Can't do that. Right? If you could change these types to something else, but that's probably not very useful for this class. Right? So in other words, if you really wanted the polar form of a point, you probably want both of these constructors. Can't do it. They have the same signatures. So what's the solution? Turn one of them into a static factory method. Right? And so you take the second constructor, the polar one, and you turn it into a static method instead. Right? The static method makes a new point2 object and returns the object back to the caller. Right? And so you might see this called the named constructor idiom, right? Because a static method behaves like a constructor that has its own name. Right? How do you implement it? It's easy, right? R theta, calculate the coordinates of the point, right? The x coordinate is just r times cosine theta. Y coordinate is just r times sine theta, right? It can't be a constructor anymore. It has to be a method. So we're going to make it a public static method, right? It's going to return a reference to a new point, so it returns a point2 reference, right? And now you give it a name. So here you could call it something like polar or from polar or something like that. Right? Anybody who knows about the polar form of a point, looking at this method, will know immediately what it does, right? Probably without even reading its documentation, right? And now you've got your constructor that can make a point given its x and y coordinate, and you've got something that behaves like a constructor that can make the polar form of a point. Right? Notice here you're going to call a constructor. You have to call a constructor to make an object, right? So here, on the last line, we're making our new point object and returning that point object. Right? And that's an example of a static factory method. Right? Very common in many types of Java classes. Right? So if you look at the source code for the course and you look at point2 or vector2, right, you'll see inside those classes there's a whole bunch of static methods. Right? There's an add, there's a subtract, there's a multiply, divide, and negate. Right? And there's also a matching non-static method. Right? Oh, okay, so there's also a matching non-static method. So in other words, there's a method for point where you would write something like p dot divide 5, right? There's also a static method where you would write divide p comma 5, right? So you call the method in a static way, right? And so you might ask, well, why is there both, right? They seem to do the same thing. They don't quite do the same thing, right? So the non-static version of add mutates the point to call the method. So in other words, there's an add method that adds a point and a vector together to give you a new point, right? So in other words, it moves the point to another point, right? So the non-static version of add, mathematically, is like writing that, right? You take your point p, so you can write p dot add v, right? So that's like taking p, adding v to it, and then reassigning it back to p, right? So in other words, it changes the point that you're adding the vector to. Sometimes you don't want to do that. I want to take p and v, I want a new point, but I don't want to change the original point. That's what the static version is for, right? The static version takes p and v, adds their coordinates together, and gives you back a new point q without changing p, right? And so there's another example of a use case for a static factory method. There's tons of examples in the standard library of these static methods. Right? So integer has a method called value of. String has many methods called value of. Right? They're all static. Right? They're all factory methods. Right? So integer value of I, that's the method that gets called when you take a primitive int and turn it into a big I integer object. Right? The compiler silently inserts a call to value of for you. Right? String.value of converts any primitive type to a string. Right? Again, example of a static factory method. Right? Arrays has this super useful method called copy of that will copy an array for you. It won't just copy an array for you, it'll copy part of an array, or it'll even make a longer array for you that's where the first n elements are a copy of another array. Right? So copy of copies that array into a new array having that length for you. And we're going to make use of this method quite a lot later on in the course. Right? String's got this method called format that will let you compute a new string that's formatted in a particular way. Right? Again, another static factory method. Right? And these things are all over the place. So if you look in the standard library classes, even the ones that we've been using so far, you will probably find at least one or more static factory methods. Okay, any questions about static stuff? That's all we need to say about static stuff. Well, that's not quite true. That's all I'm going to tell you about static stuff in this course. Right? Okay, so I think we're out of time. We'll pick this up in tomorrow's lecture.